I'm Curt Frye. This week, I want to take a break from looking at the traveling salesman problem and instead look at something called the knapsack problem. In a knapsack problem, you have a container, and in the original story it was a knapsack or a backpack, that can hold a certain amount of weight. And your goal, given different weights, which are shown here with items 1 through 17, is to maximize the weight that can fit into a container. It is a very hard problem, but you can solve it in Microsoft Excel using Solver. The sample file I'm using is called knapsack_intro, and you can download it using the link that I provide in the video description below. So the data that I've provided here, I have a list of items and their associated weights. Then the changing cells, which are highlighted here in yellow, will indicate whether a specific item is included or not. Because there is a maximum weight, I need to calculate the amount of weight that has been put into the knapsack, and that is what I'm calculating here. The goal is to not exceed the capacity, which is in cell D23, and then to maximize the included weight. So it's okay if we can't get all the way to 248, but we want to minimize the amount that is left over. I have calculated unused weight, and that's not used in any of our calculations, but it could be used if, for example, you said we can leave as much as 5 pounds empty. So that's the sort of thing that you could do with that. You can also set a minimum number of items, and I will try that later in this movie. So let's start by creating our solver model. There's actually nothing else that we need to change. So I'll go up to the Data tab, click Solver, and begin defining my solver parameters. The objective cell is D21. That's the amount of weight. We do want to maximize, and we'll do that by changing the variable cells, which I have highlighted in yellow. Those are C24 through C20. And we will use the following set of constraints to define the problem. I'll click Add. The first is that D21, which is the included weight total, must be less than or equal to the total capacity, and that is given here in cell D23. So D21 has to be less than or equal to D23. Then I'll click Add. The second constraint is that included must be either 0 or 1. The cells in column D are the weight multiplied by whether an item is included or not. So if item number 1 were not included, this would be 0, and the included weight would be 0 because it hasn't been added. So let's make the cell reference C4 through C20. And because the value can be either 0 or 1, we will define it as a binary variable. And click Add. The solving engine can be GRG nonlinear, and that's because binary, 0 or 1, is nonlinear, but it does not require us to use the evolutionary solver, which we have used for videos including the traveling salesman problem, and we will use for other knapsack problems later in this playlist. So with that ready to go, I'll click Solve, and we'll see if we can get a solution. We did, and fairly quickly, so I'll click OK. And based on these weights, it appears that we can get up to 143 out of 147. And because this is a nonlinear program, we are actually not guaranteed that this is an optimal solution. However, we were able to get 11 items in. Now let's see if there's a way that we can fit 13 items into our knapsack. So for that, I will add a new constraint. I'll go up to Solver, and then subject to constraints, I'll click Add, and that will be the cell reference of C21, the total number of included items, must be greater than or equal to the minimum items in D26. And I'll click OK. And then click Solve and see what we get. We get an error. The solver could not find a feasible solution. I'll click OK. So we can't do it with 13. We were able to do it with 11 earlier. Let's try 12. Not 21, 12. There we go. So I have 12 in cell D26, which will be our new minimum number of items constraint. I don't need to change the model, so I can just click Solver, click Solve, and see what we come up with. There is a solution. So there is a way to do it with 12 items. I'll click OK. And also, I see immediately that this is a better solution than the original. We can fit all 147 pounds into our knapsack with a capacity of 147. So that means that there is 0 left over. And that once again demonstrates that when you use the nonlinear solving engine, you might be able to find a solution, but there's no guarantee that in fact it is optimal. And here, because our criteria is the total amount of unused weight, that is the capacity of the bag, we are using all of it, so we have satisfied our ultimate constraint. I hope you enjoyed this video. If you did, please like it and subscribe to my channel.